Today is Chapter 4, Section 3, Logarithmic Functions. Alrighty, so every exponential function f of x is equal to a raised to x power for a greater than 0 and a not equal to 1 is a one-to-one function by using the horizontal line test, and therefore has an inverse function. Okay, so we are just this whole sentence basically just recapping our exponential functions. Right, it is one-to-one, and therefore it has an inverse. Okay, well that inverse is going to be called the logarithmic function. Okay, so that's about it. All right. So notice, I mean, again, this is just going back and showing the exponential function there. Some base raised to the x power is indeed one-to-one. Okay. So it has an inverse function, and the inverse function is the logarithmic function. Okay. So I'll put that here. I'm gonna write something real quick. Okay. So, do you guys remember we did? I can't remember if it was this class or another class. But if it wasn't this class, then we did talk about finding inverse functions, but maybe not recently. But in order to find an inverse function before, we had that four-step process, if you recall. Oh yeah, I do remember doing this class. It definitely wasn't anytime recent, I guess. But the way I did it was obviously different from the textbook. But again, if you recall, you changed f of x to y. We interchanged x and y. We solved for y, and then we plugged or we changed y to f inverse. Right. Well, lucky for us, we don't have to do all that for this. Okay. So I wrote down here. I color coordinated it because I feel like it does help to see what goes where. Obviously, all I did was realistically was just rewrite that. Right. Um, let's go ahead and actually read this before I move on. Okay. So if we let a be a positive number with a not equal to 1, the logarithmic function with base a, denoted by log base a, right? We read the subscript there, we call it base a. Log base a is defined by log base a of x is equal to y. And that's the same thing as saying a to the y power is equal to x, right? So we can flip-flop from logarithmic to exponential really quick if we just sit here and I color coordinated this stuff down here, right? So if you just follow along with our colors, all right, and like that looks pretty, guys, okay, especially with that green around it. But anyways, I'm saying, oh yeah, if you just follow along with the color coordination down here, going from log to exponential and exponential to logarithm, you'll do very well for the remainder of, honestly, probably this course. We've only got a few weeks left, and a lot of it we talk about logarithms and exponential functions. Okay, so anyways, so log base a of x is the exponent into which the base a must be raised to give x. Let's see, we're going to note. We read, yeah, I already said all that. Okay, good. But anyways, so again, the big takeaway is this. Right, write that down. If you have other colors, maybe coordinated as well. But realistically, once you get used to it, you'll be just fine. Okay, just again. So let's see. How can we figure out how to memorize this? I don't remember what I used to do. Now it's just so natural. I got nothing. All right, I got nothing. You have to figure out how you want to memorize it. Same thing I did there. At least I made it pretty. Look, look, mine is way prettier than that. What is this? Base exponent garbage. All right. Here we go. So example 1. So today is going to be one heck of a snip day. Look, it seems to be a trend, right? So example 1, logarithmic and exponential forms. So the logarithmic and exponential forms are equivalent equations, right? So they're equivalent. They're just written differently. If one is true, then so is the other. So we can switch from one form to the other, as in the following illustrations. Okay, so let's go ahead and we'll look at these one at a time. Okay, we're going to look here first. All right, so this 10 would be the base. We're going to raise it to this 5, and that is equal to the argument. Oops, I'll go a little happy on my comma there. That's equal to the argument, right? And of course, that's what we see over here. Right? I mean, I don't necessarily feel like I have to write it out for each one of them because I mean it's already written, right? I'm just rewriting it. But I will do this one because you know, like nobody likes negatives or fractions. This has both. So let's look. The argument here, 2. Okay, it is raised to the negative 3 power, and it's going to be equal to the argument, which is 1/8. Okay, and that makes sense, all right? Because 2 to the negative 3 power, 2 to the negative 3 power, that's equal to 1 over 2 cubed, which is going to be 1 over 8. And of course, that again, that is the solution. Okay, but anyways, take some time because I mean I know you've come across logarithms before. Okay, but again, logarithms is just another one of those things like piecewise defined functions. Or again, when I was a student taking this, I would just like in one ear out the other, whatever. So I didn't really memorize anything. But take the time to memorize that down there in the bottom, nice and colorful, and then you know make it become natural to you, and then for problems like this, just make sense of it, right? Kind of like write out what I did. You know, I said, you know, okay, base 2, you know, raised to the over here, negative 3. So just make sense of all this because we're learning the properties now, but we're learning the properties so we can solve equations later. So become very familiar with it before we get to that point, right? Otherwise, you'll be kind of screwed. I'm gonna snip this and put it on the same page. If it'll fit. Okay, yeah, it fits. All right, so that's nothing. I mean, it's just showing properties there. I don't feel like that's necessary for me to go over. Right. And then this time we're going to be going the other way. Right here. Okay. So, are we going the other way? Did log to exponent? No, not really. That's actually the same procedure, right? Again, let's look at we'll do C. We'll do C. Okay. So this 10 is the base, right? So that's going to be the base. That's going to be a big number. It's going to be raised to the negative 1 power. What was that? Oh. I don't like that sound. Let me finish this and I'll be right back. 10 to the negative 1 power, and that is equal to, again, the argument, which is 0.1, right? And that makes sense because 10 to the negative 1 power is 0.1. Anyways, be right back. All right, I'm back. I don't even know what I was looking for. I just heard a sound and I went to investigate. So whatever. Anyways, example 2, same example 1. Just make yourself familiar with the anatomy of logarithms and their exponential form, right? 16, base 16 raised to the 1/2 is equal to 4. Yep, that's exactly what that is, right? So make sense of these examples. be able to convert exponential to logarithm and logarithm to exponent or exponential. Make it a quick process, I promise. It's going to be necessary for the upcoming stuff. And on top of that, I did say before that chapter 3 is probably the hardest thing that we've done and that we will do in this course, and that's true. But this is, it's also, oh actually, no, let me take it back. Chapter 3 was tedious. This might be a little harder, but I feel like it's easier to understand, right? You don't have to go through the tediousness of, factors of this, factors of that, putting here, putting there. If you just basically memorize what I wrote on the first page all colorfully, you'll be just fine. Okay, we did talk about this, but we're talking about it again, so it must be relevant here. Okay, so we've talked about the inverse function property. If you take the composite of f inverse of f of x, you should get x, and then if you take the f of f inverse of x, you should get x as well. All right, we have talked about that before, and that tells us that two functions are inverses of one another. What I mean, so where have we seen this before? You might have had a problem that had f of x be equal to some function, and you had g of x be equal to some function. And the problem that you might have encountered regarding this is it would say show that these two functions are inverses of one another. And in order to show it, you need to do the composite f inverse of f of x and f of f inverse of x. And if you get x in both cases, then those two functions are inverses of one another. Okay, so I know we've covered that before. Don't know where, but if you need a refresher, obviously my playlist, go check it out. Like, subscribe, donate. But anyways, what was I saying? Oh, I need coffee. Dang, I really forgot what I was saying. Alright, it's just one of those days. Okay, so here we go. Properties of logarithms. Now, the properties of logarithms, they are, we'll put it right here. Yeah, we'll put it right here for now. Okay, they are common sense. Okay, so let's start with property 1. It says log base a of 1 is equal to 0. Okay, that's fine. All right, so let's make sense of it. If we took this and put it in exponential form, that would be a to the 0th power is equal to 1. And that makes sense, right? Because anything to the 0th power is 1. And if you forgot why that is the case, let's cover that real fast. Okay, so let's do this. 1's going to be equal to that, right? Do we agree? 1 is equal to anything over itself, right? Well, we know that using our exponent property rules, that if we're dividing, we can simply say x to the m minus m. Maybe I should have picked a better letter than an m, right? And then m minus m, well, that's just 0, right? Right? So that's why anything raised to the 0th power is 1, because the same properties that we've talked about before, that they come into play, and so anything raised to the 0th power is 1. So again, property 1 here, common sense, right? So let's go to property 2. All right, so property 2 here, we have a raised to the 1st power is equal to a, right? That, again, I'm just taking this logarithmic form and putting it in exponential, and that makes sense, right? Anything raised to the 1st power is itself. Okay, so that's pretty common sense as well. Okay, well now 3 is starting to look a little ridiculous, so let's go ahead and look at 3. All right, so that says a to the, okay, again, I'm looking over here, a to the what, x power is equal to my argument, which is a to, oh, well, it turns out it's not that ridiculous looking, is it, right? I mean, it looks silly, but again, it makes sense. A to the x is indeed equal to a to the x. Okay. Now the last one does look ridiculous. Okay, but realistically, the reason why it looks so ridiculous is because the first three, we're starting from logs. Okay, the 4th one, we're starting on exponential. So let's actually write the 4th one in exponential form. Okay, so this would be log base what? Base a, right? Because that's the base there. Log base a. Okay, and then that is equal to. Okay, well, what is that equal to? Log base a of x. Okay, so we've got. Well, shoot. Sorry. Like that. It should be that. I'm sorry. So we have the exponential base, which is a, so that's going to be log base a. Log base a of what? Of a is equal to the x over here. And again, this is going back to this. I'm changing from here to here, right? It is log base a of, again, the argument, and that's equal to my the exponent I have there, right? The argument goes next to the log, and that is equal to my exponent. Okay. So again, the first three I'm going from log to exponent, but the fourth one we're gonna change it from exponent to log. Okay. So hopefully that makes sense. And then the example 3, it's not really an example. I mean, I guess it's an example. It's just not an example we have to work out. Similar to the first two. It's just like, hey, we're gonna slap an example on this and tell you. Okay, but anyways, so let's go ahead and look at the example, I suppose. Like so. Okay, so we see that this one. Oh, we see that this does indeed follow property 1, right? It's 5 raised to the 0th power. I'm sorry, log base 5. Well, I mean, it would be. It'd be 5 raised to the 0th power is equal to 1. So yes, we do indeed follow property 1 there. And then you can follow along and just kind of put the puzzle pieces together and see where property 2, property 3, and property 4 also just follow along with the properties above. Okay. All right, now the graphs. So this is we'll do this. We'll just go and graph it or snip it and then talk about it. Alright, so graphs of logarithmic functions. So it reads, recall that if a one-to-one function f has domain A in range B, then its inverse has domain B in range A. Okay, remember they were opposites there. Remember, again, I'm pretty sure this was the last lecture. Since the exponential function f of x is equal to a raised to x power, okay, so we're to look at this. This is the exponential function. Okay, it's got domain of all real numbers and a range from 0 to infinity. So this is this blue line right here. Okay, well we've already discussed that logarithmic functions are inverse functions. So before we even read the rest of this, okay, we know that inverse functions, okay, they're inverse about this line right here, y is equal to x, and so basically we just mirror across that line. Okay, so this red line would be the logarithmic function, obviously a lot more precise. So, and honestly, that's about what it says. Okay, something. So let's actually do this. So, let me make sure the definition doesn't take care of it for me. Okay. Well, it doesn't. All right. So we'll do it. All right. So, let's put it. Let's draw this over here. Okay, so here we go. The domain of f, okay, is negative infinity to positive infinity. The range of f there we go, is from 0 to infinity. Okay, and again, without even looking over here, without even looking there, I can say that the domain of f inverse, don't get just a bunch of dots there. there we go, f inverse, again, is the range of f, right? It's going to be 0 to infinity, and then the range of f inverse is going to be that domain of f, which is negative infinity to positive infinity. Okay, and then I, for once in my life, actually color coordinated along with the textbook, right? So blue is f, my a raised to x power, and red is my logarithmic function, log base a of x. Okay, so another important thing, especially when we talk about transformations of logarithmic functions, if you recall, I had what I called landmarks. Okay, landmarks for like the first 9 parent functions was always my origin, 0, 0, right? Because square, x squared, the cube root, everything basically ran through 0, 0. Okay, well, we talked about the landmark for exponential function being at 0, 1. Okay, well, the landmark for our logarithmic function is going to be the point mirrored across that line y is equal to x. Okay, so we're going to use the point 1, 0 more or less as the landmark whenever we transform logarithmic functions. Okay, so this is just a sketch the graph kind of thing. So the first thing we're going to do is we're going to go back to 6th grade, and we're going to make a table. Actually, I can probably put both of these on here. We'll make a table, and then we will plot those points on the table. Okay. But obviously we know better. We're going to figure out, okay, so once we know the anatomy of the exponent or the logarithmic function, which is what example 4 is showing you, once we know the anatomy of the logarithmic function, then we can start doing the transformations. Okay, and again, this particular graph is just basically what we saw on the previous page, right? We're cutting through the point 1, 0, and then we're just slowly going this way forever. Okay. That's really about it. Again, this example is all about the anatomy of the logarithmic function. We need you to understand what it looks like and how it behaves. All right. As far as plotting points, we're done with that. Just showing it for this one example. Excuse me. That's interesting. Okay, so we'll put this in there as well. Can I fit that though? Let's see here. Yeah, we can fit it. There we go. So obviously figure 4 shows graphs of the family of logarithmic functions. So notice how every one of them do indeed go through the point 1, 0, okay? And the only reason why it looks like we are even, we have different angles we're coming out of that point for is because our bases are different, okay? So our base determines just how sharp we turn. Yep, that's about it. Just read that, make sure nothing more important. Okay, so we're just going to discuss this, and then I'm going to snip the prettier graph. Okay. So new page. So A is again, what's the parent function? Obviously, our parent functions today, they're all going to be logs, right? All right. So we know that my logarithmic function looks something along the lines of this, right? Obviously, well, let's be a little more precise, I guess. Okay. So this looks something like go through 0.10, and then we shoot off. Okay. That's what our logarithmic function looks like, right? Okay, well, we're going to follow the same rules of transformations with logs that we do with everything else, literally everything else. Okay, this is the negative of the function. Okay, well, if you have the negative of the parent function, then if you recall, what you do is we reflect about the x-axis. I just got a message talking about my audio. I really don't know. I bought 2 separate headphones because my first one, because my computer actually messed up over fall break. my one I started with, and I bought two separate headphones for this computer because that headphone didn't work. I'm at a loss. I really am. The YouTube video seems to be fine, so maybe we'll maybe hopefully that's better. I don't know. But I do appreciate you telling me. But anyways, so A, again, what we're doing here is we are reflecting just about the x-axis. Okay. Well, B. Okay. Well, so if we were to, can we just, yeah, there we go. If that were, again, that's my normal function, right? My normal logarithmic function. Well, B will be reflecting about the y-axis. Okay. So we're going to go this way. We're going to cross to the point -1, 0, and we're going to shoot the other way. Okay. So before, well, not before, but let's actually go ahead and just show you. I mean, we won't have to talk about it there, do we? There we go. Okay, so this is obviously a better representation, a lot prettier than what I did. Okay, but I did obviously want to draw it and just give an idea of the thought process as opposed to saying, hey, here it is. So again, we can see that my parent function is here, and then this is for A, and then reflect about the x-axis, and then for B, this is my parent function, and then we reflect about the y-axis. Same thing with shifting. We follow the exact same rules as before. Okay, so for A, it looks like we're going to be going up 2 units, and for B, let's put A here, and for B, it looks like we'd be going, okay, now it is an x minus 3, so this tells me I'm going to go to the right 3 units, and that's really it. And so let's we'll do, this is A. And this is B. Oh, we have to do domain range and asymptote. Sorry about that. Okay, so let's we'll put A there, B here. We'll denote that. Okay, and again, you can see that we do indeed go up 2 units for A, but again, the landmark is not 0, 0. It's not 0, 0, right? It is 1, 0. Okay, and we will go up 1, 2, and then my new landmark is right there. Okay, so remember that. And the same thing here, if we shift it to the right 3 units, we go from 1, 2, I counted wrong, let's try it again. We go 1, 2, 3, and again we do indeed shift right 3 units. Okay, let's talk about the domain, range, and asymptote. Alright, so for A, again, this is just something we can just chit chat about, right? Well, what's the domain of the logarithmic function? Okay, well it's going to be from 0 to infinity, right? Because I mean, first of all, you can just kind of tell. You can kind of tell, it's 0 to infinity. But remember that it is the range of the exponential function, which is 0 to infinity. Okay, so realistically, the domain and range are all the same on these two problems. The domains is from 0 to infinity, and my ranges are from are all real numbers. Okay, and for A, the asymptote, it looks like. Actually, I'm at x equals 0. Yeah, I suppose this would be our asymptote. X equals 0 would. I'm an idiot. X equals 0 is indeed the asymptote. Okay, and because we let's do this. I don't feel because mainly because this isn't going all the way down. We know that this logarithmic function goes all the way down. Gets infinitely close to 0 without actually touching it, right? So x equals 0 is going to be my vertical asymptote for A. So we'll put it in blue. Put vertical asymptote, and that's going to be x is equal to 0. Okay. Well, what about, well, B is actually already is actually drawn on there for us, right? But we can imagine if we moved this blue line, to the right 3 units, we're basically moving it from the asymptote being x equals 0, and we're moving it to the right 3 units, so my asymptote is going to be at 3. Okay, so that's the domain, range, and asymptote there, and I believe that covers it. Yeah. Again, just know that the anatomy of the logarithmic function, and we perform the exact same operations that we are used to. Okay, so common log. Alrighty, before we touch on common log, if I do this, if I just do that, okay, we know that's the square root. We know that there is an implied 2 there, right? We don't write it every time, but we do know that there's an implied 2 there. That's the same thing with common log. All right, look here. That just simply says log x, okay? If there is nothing, if we have no base given to us, then it is an implied 10, and that's it. Maybe I shouldn't have given it its whole page. Let's see what we got. What else we got for common log? I mean, I'd say same thing. We're gonna see what it looks like, right? It says use a calculator, so we're just gonna snip. I wonder if that'll all fit by itself. Oh yeah, we'll fit. Okay, so same procedure that we did before, but this is just they're just evaluating with the base 10. That's really it. Which, by the way, your calculators default to base 10. Okay, now we're gonna have problems where we solve. We might have a problem that's like this. Log base 7 is equal to like 9, something like that, right? 7 raised what power is equal to 9. The thing is, you're not going to be able to do that with your calculator just yet, unless you read ahead. Okay, we'll have to do what's called a change of base formula. Okay, because some of your calculators might be a lot more advanced, and you can actually change the base. But for the most part, you are sticking with a base 10, and you got to go from there. But like I said, we will be able to deal with logs that are not just base 10, but that will be later on. But anyways, example 7, just plug in x into log of x, and then we get our y's back. Okay, so we have x, y's, and then we plot the points. Again, same thing. We're just showing the anatomy of the common log, which is the same. It's just a lot more more of a sharp turn. Okay, so all this needs to go together. I actually kind of have a problem to work today. That's interesting. But just slightly. So much so that I'm also just going to, I'm just going to also snip. Do I have room? Yeah, we have room. Have to shrink that a little bit though. Okay, so with all word problems, it's not the mathematics that is the tough part. The tough part is basically connecting the dots of your word problem. What I mean by that is figuring out what each variable is saying and what we're looking for. Okay, so let's look at this. All right, so starting over here, it reads, scientists model human response to stimuli such as sound, light, or pressure using logarithmic functions. For example, the intensity of a sound must be increased many-fold before we feel that the loudness has simply doubled. The psychologist Gustav Fechner formulated the law as S is equal to K log I over I naught. Okay, where S, okay, so this is a big deal. So S is going to be the intensity, or it's a subjective intensity, right? So I guess it's all different for us. It's going to be the subjective intensity. I is going to be the physical intensity, and I naught is going to stand for the threshold. Stand for the threshold physical intensity. Okay, I feel like it should mean of threshold, whatever. I naught stands for the threshold physical intensity, and K is the constant that is different for each sensory stimulus. Okay, so we've got 1, 2, 3, and essentially 4 unknowns here. Okay, again, just the anatomy of it. This is how I would break it down if I was looking at it. Obviously, I know, but I know the problem's a lot easier. But I would look at that and be like, okay, so we got 1, 2, we got 4 unknowns. Okay, okay, so human rough. Okay, so here we go. Let's actually look at the example now. So the example reads, the perception of the loudness B in decibels of a sound with physical intensity I in W. We don't. Well, whatever. Is given by, and of course this is our equation. Okay, so let's examine this equation. The thought process is we have B is equal to 10 log, and then I over I naught. Okay. Now I probably shouldn't have put the solution here actually. Not yet, because I really want to do a thought process before we actually get to it. Okay, where I naught is the physical intensity of a barely audible sound. Find the decibel level and loudness of a sound whose physical intensity I is 100 times that of I naught. Okay, so how would I write? You can probably see underneath it, but if I said, I got it. Okay, if I said that I am my level of happiness is 3H. I'm 3H happy. Okay? And let's say that you, as a student, you are actually loving my course, but you are 100 times happier than me. How would you write that? Okay? Well, I know it doesn't. I know it sounds too easy to be true, but you really just say, okay, well, if Sherman is 3H happy, and I'm 100 times happier than he is because I love his voice, then I would just say 100 times 3H. Okay, and therefore, obviously, you are 300H happy. Guys, that was an example on the fly. I really hope that one sticks. Okay, because the same process happens here. Ooh, okay, there we go. My computer kind of slowed down. Okay, so if we're looking at something that is 100 times out of I naught, well then what you do is you just simply replace you replace I with 100 times I naught. Again, like 100 happy, right? So then you have this is our original equation, and then we're going to replace our I with 100 times I naught. Again, 100 times I was going to say happy. 100 times that of I naught, okay? And then of course, and when we plug that into our equation, we put it right in the numerator, and we just do the algebra. The I naughts cancel. Then we have 10 log 100. And let's actually look at this. 10 log 100. Look at log 100. Okay, so log 100. Log 100. Okay, well what does log 100 equal to? Okay, well obviously it's 2, but how do we get to 2? Okay, well let's again imagine that, again, the base here is implied. It's implied, but it's a 10 there. So, and again, this is maybe just a preview of the next section, but 10, let's do this. Okay, so if we were to take this logarithmic form and put it into exponential form, we might say, okay, so 10 raised to what power is equal to 100, right? Again, 10, and then the question mark, and that's equal to 100, right? And again, this is from page 1. Remember the colorful thing I did? Well, 10 raised to what power is 100, and we know that's to be 2. 10 squared is indeed 100. And that's where we get the 2 right here. Okay? And then of course the 10 out front, 10 times 2, so 20 decibels. So I forgot what the question was asking. I forgot to find the decibel level whose physical intensity. So I guess you can start feeling the physical intensity of sound at 20 decibels. Okay. So takeaway from this particular example, it is a word problem, okay? But again, the hardest part of a word problem is actually breaking it down and figuring out what they're being asked, okay? And for this particular one, and I'm pretty sure you'll have one of these on your homework or something. But if something is 100 times that of something else, again 100 times happiness, right? Then it's as easy as you think it is. You just simply say 100 times I not, which is right here. Okay. Second takeaway, and again, this is something we'll definitely harp on in the next or in the upcoming sections, was changing this log of 100, changing it into a 2. Okay. Okay, so we had the common log. Pretty sure we're getting to the natural log. There we go. Next, we're going to talk about the natural log. We're going to put this first, and then we're going to put this note second. Is that fit? we might can make. I think we can make that fit. Yeah, kind of. We'll make it smaller. Yeah, that's fine. Okay. So let's start over here first. All right. So natural logarithm. So the logarithm with base e is called the natural logarithm and is denoted by. Oh, that is it. Is denoted by natural log x, just simply ln x. Okay. Now again, so let's see here. So if we had, when we've seen this before, log, base 7 of x. Okay, well that's just log base 7. Okay, and of course if we don't put a base, then that's an implied base 10. Okay, well now if my base was 2.71828, okay, we know that is simply the log of, and of course 2.71828 is an approximation of e. Okay, so that's log base e of x. Okay, but instead of writing log base e of x, we simply just write natural log. Or, and the reason why I put that note there is because whenever every time I write ln in my head, I always go log natural, right? But of course, naturally, it comes from the Latin name Logarithmus naturalis. Okay, and that's where the ln comes from. But anyways, this is how, and I'll keep this down here. This is how we go from log base 2.71828 of x, okay, which is the same thing as saying log base e of x, and we just simply write that as natural log of x. Okay, and that's all the natural log is. And the natural log is going to, the anatomy of it is the exact same as your normal logarithmic functions. Okay, it's just that this turn happens because my base is 2.71828. Okay, so it'd be very close to something that looks like log base 3, right? And not as close to something that's log base 10 because 2.71828 is obviously closer to 10. That about sums that up, I believe. Ooh, the properties. Okay, so the properties. Okay, so example 9 isn't done the same way as we saw earlier, but we'll snip. Okay, so these properties are the exact same properties that we saw earlier with logs. Was that long ago? Oops. This. All right, it's the exact same properties that you see here. Okay, except this is with a base of some a, right? And then this would be with the base e. Again, the same principles. Okay. So example 9, we just evaluate with the calculator. Again, similar to what I said the last time we talked about the number e. Make sure that you can that your calculate when your I'm not gonna say it does. If you have a scientific calculator, or I mean definitely above a scientific calculator, you'll have e. But get very, and I mean very familiar with using it. We're going to be using it a lot when we start solving equations involving not just logs but also natural logs. Okay, and of course, and that's about it for that. Those examples you can follow along with pretty easily. Okay, so actually I didn't want to do all of that. Finally, I can do some computation for today. Okay, so this reads, find the domain of the function f of x equal to the natural log of 4 minus x squared. Okay. So, first of all, we have to ask ourselves, what is the domain of a natural, what is the domain of a logarithmic function? Okay, let's go back real quick to this page. Okay, and again, remember that this is the domain and range of exponential functions. Okay, and I probably should have noted that, huh? A raised to the x power, and this would be log base a of x. Ooh. Let's try that again. This will be log base a of x. Okay. All right, so in the blue, you'll see the domain and range of exponential functions, and in the red, you can see the domain and range of logarithmic functions. Okay, and again, they are just opposites of one another. The domain of one is the range of the other, and the range of one is the domain of other. But anyways, what we're focusing in on is this, the domain. Okay, this is again the domain of a logarithmic function. It is from 0 to infinity, strictly greater than 0. Okay, so the domain of logarithmic functions have got to be greater than 0. So we're going to use that here. Okay, so this argument, okay, it's called the argument there, must be greater than 0. So let's write that. So we're going to write 4 minus x squared has got to be greater than 0. Good. Okay. Well, how do we do this? Okay, so this is pretty easy, right? This is a difference of squares, right? This is an a squared minus b squared. Okay, so we can essentially write this as 2 minus x and 2 plus x is greater than 0. Perfect. Okay. So what does this tell me? This tells me that x is going to be, and again, we have to solve this similar to whenever we had like a second or third degree polynomial inside, or well, I guess maybe third. I don't know. A polynomial of greater than degree 1 inside of a radical. Okay, and what I mean by that is this is the number line. This is making a number line problem. Okay, so let's go ahead and start on that. So actually, so x is going to be equal to plus or minus 2. Okay, so now we got to write this. We got to draw a number line out. Do that every time. Okay. All right. So we're gonna make a little wall here at denote that as -2. Denote this as +2. Okay. So this is -2. This is +2. We're gonna write our intervals. So the interval on the left side over here is from -infinity to -2. And from -2 to +2, and then from +2 to infinity. Okay, so we're going to have a test point. So we're going to have a test point being -3 here. I don't actually like this being so close. Maybe we can put that, maybe we change the color. We'll say x is equal to, changing the color helps. Anyways, so we're going to use the test point of -3, a test point of 0 because it's there, and a test point of positive 3. Okay, so hopefully you remember us doing this. All right, so what I'm going to do is I'm going to plug in negative 3 in for x here and here. Okay, I don't have to do any computation though, because I know that a negative times a negative is a positive, and a positive times a negative is a negative, and of course a positive times a positive is a positive. Okay, so I'm looking for numbers that would be greater than 0. So let's begin. If I plug in a negative 3 here, okay, well 2 minus a negative 3, that's a positive 5. Perfect. So this is going to be a positive number. Let's make it nice and thick. A positive number. All right, but 2 plus a negative 3, that's going to be a negative number. Okay, well positive times a negative is a negative, and a negative is not greater than 0. So this interval does not work. Next up, we're going to plug in a 0. Okay, well 2 minus 0 is 2. 2 plus 0 is 2 minus 0 is 2, which is positive, and 2 plus 0 is 2, which is also positive. So we have a positive and a positive times a positive is a positive. So good. And then lastly, we've got 3. So 2 minus 3, that's going to be a negative number, and 2 plus 3 is a positive number. We have a negative times a positive again, which is a negative. So this interval does not work either. Okay, so therefore the domain of this particular problem is simply negative 2 to positive 2. Okay, we'll draw that out here. The domain of f is simply negative 2 to positive 2. Okay, hopefully I didn't lose you there. Again, this is just something that we've done before. Is it tedious? Lord, yeah, it's tedious, but you just gotta do it. And that's actually pretty crazy that this particular domain is from negative 2 to positive 2, and so we see that in this example here. So this says, actually, let's see if if there's more down here I can get. Yeah, we'll snip that and then we'll be done. Okay, so this particular example it reads, draw the graph of the function y is equal to x times natural log of 4 minus x squared, and use it to find asymptotes and local maximum and minimum values. Okay, so drawing it, we were going to put this in a calculator. There is, yeah, there is a way to figure this out, to actually draw this on our own, and it's actually pretty easy. But again, we need to learn how to actually solve and get rid of our natural logs and stuff before we can actually even draw it, free-handed, right? Free-handed being like, if I gave you, x cubed plus 3 or something, you can envision that in your head. Whereas this, maybe not so much until we at least figure out how to solve them algebraically. But anyways, so if we graph it, it wants us to find the asymptotes and local maximum and minimum values. Okay, so if we graph this, we can see that, well, first of all, the domain was from negative 2 to positive 2. Okay, so that tells me right away that at, maybe make it blue, right here at negative 2 and right here at positive 2, we're going to have us some vertical asymptotes, right? And of course that's what it reads here. Local maximum and minimum values, and obviously this is, well, calculus could figure this out, but we don't know calculus yet, do we? So you use your trace thing, and hopefully I'll make sure that there's anything like this on the test. I mean, there will be homework problems like this. I want you to know how to do things and understand them. But as far as like the test goes, I nothing like this is gonna be on the test because I really hate calculators. But anyways, that's about it. You can see your local minimum is located here. It looks like it's at what? Negative 1.15. That's what it says there anyways. And then right here it would be our local maximum, which would be about 1.15. So again, example 11 is just going to be one of those examples where we pull out our calculator, we figure things out. It's necessary. It's 100% necessary. Okay, so don't get me wrong when I say I hate calculators, because you need to understand the anatomy of what you're actually looking at, right? But as far as the computation is concerned, for tests, I hate calculators there because it's such a crutch. Okay, I want you to understand what you're looking at, but when it comes to solving problems, I hate the crutches. even though I do allow calculators. Anyways, that will conclude today's lecture.